Welcome to the Explainer. Today we're diving into a genuinely fascinating breakthrough in material science, the creation of a high-tech, multifunctional magnetic rubber. Think about the devices we all use every single day, right? Our phones, our smartwatches, our cars. They're getting smaller, they're getting more flexible, and honestly, they're becoming incredibly complex. To make all of that happen, engineers are constantly hunting for materials that can do things that seem completely contradictory. Like they need something as flexible as a simple rubber band, but it also has to be magnetically responsive and incredibly strong. So let's dive into exactly how a team of researchers actually managed to engineer this apparent paradox. But before we get into the heavy chemistry of how they pulled it off, we need to ask ourselves a pretty fundamental question. What actually happens when you try to force metal and rubber to behave as one single material? I mean, it's not as simple as just stirring some metal dust into a vat of liquid rubber. In fact, traditionally, when you add enough metal to rubber to make it magnetic, you ruin absolutely everything that makes rubber useful in the first place. It gets brittle, it clumps up, it loses its bounce. The real challenge here is figuring out how to get these two completely different worlds to cooperate. So here's our roadmap for today. 1. The quest for better rubber. 2. Meet the magic ingredients. 3. The Goldilocks zone. 4. Handling the heat. And 5. Future tech applications. Okay, Section 1, the quest for better rubber. Let's look at our baseline. Let's see how this builds from the ground up. Our starting point is a blend of two very specific polymers, NBR and EPDM. Now, NBR is famous in the industry for being incredibly resistant to oils and chemicals. Meanwhile, EPDM is the absolute superstar of weather resistance and thermal stability. So, you blend these two together, and you get a wonderfully tough, oil-resistant rubber that can survive some seriously harsh environments. But here's the catch. It severely lacks the mechanical strength and the advanced functionalities, like magnetic responsiveness, that are absolutely required for modern next-generation tech. Basically, it's tough, but it's just not smart. Moving on to Section 2. Meet the magic ingredients. To give this basic rubber blend its high-tech superpowers, we need to introduce our first highly engineered ingredient. It's a copper-aluminum-zinc ternary alloy powder. And on a microscopic level, these alloy particles have these jagged, heterogeneous shapes. The specific alloy was chosen because it provides incredible, soft magnetic behavior, meaning it's super easy to magnetize and demagnetize. But as we mentioned just a minute ago, if you just dump this metal powder into rubber, the particles naturally want to clump up together. They agglomerate. And when they do that, they create these massive weak spots that completely ruin the rubber's flexibility. To solve that fatal clumping problem, the researchers had to get pretty clever with their chemistry. Enter our second vital ingredient, TMSPM. It's a psyllium-based coupling agent, but you can think of it simply as a high-tech molecular glue. What TMSPM does is it coats those microscopic metal particles and chemically forces them to bond with the surrounding rubber matrix. It essentially forces the metal and the rubber to hold hands tightly, making sure the metal spreads out perfectly evenly instead of clumping up into a brittle mess. If we look at the ATR-FTIR spectrum, which is basically a chemical fingerprint, we can actually verify this molecular glue at work. You've got these very specific peaks on the graph, like the ester stretch at 1709, or the silicon-oxygen vibrations around 1057. And they verify its unique chemical structure. This is the exact signature of the vital interfacial adhesion that allows the rubber and the metal to become one unified composite. So how do they actually put all this together? Honestly, think of this process exactly like high-tech baking. First, they take our base dough, the NBR and EPDM rubber blend. Then, they carefully fold in our special magnetic alloy ingredients, along with that TMSPM molecular glue. And finally, they bake it. They throw it into a hydraulic press at about 152 degrees Celsius under intense pressure, a process called vulcanization. This heat and pressure cure the rubber, locking all those cross-linked molecular bonds firmly into place. All right, Section 3, the Goldilocks zone. Now, just like your favorite recipe, the proportions here matter immensely. Adding too much or too little alloy completely ruins the final product. The researchers tested several batches, slowly dialing up the amount of metal. We can see this Goldilocks effect clear as day when we contrast two specific batches. On one hand, we have the Ne3 blend, which uses 10 parts of alloy. This turned out to be just right, efficient, incredibly strong, and perfectly magnetic. On the other extreme, though, we have the Ne8 blend, where they aggressively overloaded the rubber with 35 parts of alloy. And this batch was a disaster. the metal overwhelmed the glue, caused huge clumps, and the material became sluggish and structurally weak. The raw data tells the story of this crucial balance perfectly. Our baseline rubber with zero metal, Ne0, has a tensile strength of just 1.91 megapascals. But look at our Goldilocks blend, Ne3. The torque, which measures how well the network resists deformation, jumps up to 12.45, and the tensile strength literally skyrockets to 4.96 megapascals. It is vastly stronger. But if we get greedy and we push the metal content way too high like an Ne8, the numbers actually drop. The tensile strength falls back down to 3.55, simply because the metal clumps together and creates structural flaws. The secret to why Ne3 is so amazingly strong comes down to a concept called cross-link density. Imagine the inside of the rubber as this dense, three-dimensional fishing net. When you have the absolute perfect amount of metal and glue, like in Ne3, the metal particles act as strong, tightly tied knots in that net, making the whole structure incredibly resilient. But in the overloaded Ne8 blend, there are too many massive metal clumps, and they actually end up tearing huge, weak holes in that internal 3D net. Section 4. Handling the heat. Creating a strong magnetic rubber is a fantastic achievement, for sure. But it's really only half the battle. If we actually want to use this in modern electronics, it has to survive the extreme temperatures those devices generate. To test this, researchers put the material through thermal analysis, tracking how it behaves as it's heated to extreme degrees. And what they found is amazing. The metallic particles in our Goldilocks Ne3 blend actually act as physical barriers. They successfully delay heat transfer and restrict the polymer chains from breaking down prematurely. The basic rubber burned up much faster, but the Ne3 blend stood its ground. To put a specific number on it, the Ne3 blend boasts a massive enthalpy of fusion at 142.7 joules per gram. What that means in plain English is that it takes a massive amount of heat energy to melt or break its internal structure. Thanks to that molecular glue stabilizing everything, it manages to hold its form under heat without becoming rigidly brittle. It stays tough, but crucially, it stays flexible. And finally, Section 5, Future Tech Applications. So what does this all mean for you and me? Well, because of its unique blend of flexibility, strength, thermal stability, and magnetic responsiveness, this Ne3 composite is an absolute game changer. It is tailor-made for next-gen tech. We're talking about flexible magnetic components for wearable electronics that naturally move with your body. We're talking about adaptive damping systems in vehicles that dynamically absorb vibrations, and perhaps most importantly, lightweight EMI-absorbing materials. EMI is electromagnetic interference. It's what happens when all our closely packed electronic devices try to scramble each other's signals. This rubber has the exact dielectric profile needed to absorb that interference, shielding our devices and keeping everything running smoothly. The successful creation of this copper, aluminum, zinc-reinforced magnetic rubber proves that by perfectly combining the right ingredients, we can completely break the boundaries of traditional manufacturing. We can make a rubber that's strong like metal, yet bends like an elastomer, all while holding a magnetic charge. But it leaves us with a pretty fascinating thought to end on. As our technology demands devices that are ever more flexible, invisible, and deeply integrated into our daily lives, what crazy, seemingly impossible hybrid material are we going to have to invent next? Thanks so much for joining me on this explainer, and keep questioning what the world around you is made of.